In this video, we'll discuss parametric surfaces and their areas. So the idea is similar to what we had when we had vector functions depending on a single variable or parameter, giving us curves in the plane or in space. Similarly, if you have a vector function r that depends on two variables u and v, so each of its components of these vector functions are functions of two variables u and v, then in general what you expect is that this position vector r, u and v will trace out, will give you a surface in space as u and v changes over the domain where they are defined. So what we have, imagine you have some domain in the uv plane, so some domain D, and as uv varies over this domain in the x, y, z coordinate system, the vector r u v will, with its endpoint, will trace out some surface. Okay, so that's the idea behind parametric surfaces. So let me just give you an example. So try and identify what surface you get if you take the vector function r, u and v with components 2 times the cosine of u, v, and 2 times the sine of u. So pause the video and give your answer below as to what this surface should look like or would look like. I hope you paused it and realized that what we have here, if you look at the x and z components, so they depend on u and v, but if you take their squared sum, what you get here is 4 cosine squared u plus 4 sine squared u, which is just 4. So what you have there is, in the xy plane, is a circle of radius 2, and in fact, for it, since it does not depend on y, the y component, for any fixed y you get a circle, any fixed value of y you get a circle of radius 2 with its center being on the y-axis, and y is just the parameter v, which can take any values. So what you really have is a cylinder, is the surface of a cylinder with the axis, with its axis being the y-axis. Okay, so, and its radius is 2. So you get something like this. Okay, so for this surface. All right, so let's now look at how we can talk about tangent planes to such surfaces given to us by vector functions of two variables. So imagine as you change in the u direction, keep v fixed, what you will have, you move that point around the u direction, what you will have is this point will move along some curve where u is changing and y is being fixed. So that means you move in just along a curve. So when you take the u derivative of this vector function, differentiate each component with respect to u, what you get is a tangent vector okay, which would be your R sub u. Similarly, if you decide to move in the y direction within that domain and keep your u value fixed, then you will get some other curve where u is, well, on the surface, where u is fixed and v is changing. Then r, u, v will trace out another curve on the surface for which the derivative of r with respect to v gives you another tangent vector at that point. Okay, so this is what you have to imagine. You have those curves on the surface. As you draw the tangent vector to those curves, you will get, by differentiating r, u, v with respect to u and v, you will get two vectors which span the tangent plane to the surface at that particular point. So what I'm getting to, or trying to say, is the cross product of ru and rv, these partial derivatives of our vector function, will give us a normal vector to the surface. And it's a normal vector for the tangent plane to that surface. And that normal vector can be used to write down an equation for the tangent plane. So let me just give you an example. Let's find the tangent plane, the equation, well, an equation for the tangent plane to the surface given to us by the vector function whose components are x equals u squared, y equals v squared, and z equals u plus 2v. And the tangent plane should be found at the point where u and v are equal to 1, 1. So on the surface, that means you have the point 1, 1, 3 in terms of x and y and z. Okay? So pause the video and input your answer for the equation of the tangent plane below. Okay, I hope you paused it and computed these derivatives. So r sub u is just differentiating these components with respect to u and writing down the resulting vector. So the y component does not depend on u, so there is no j vector in this sum. The z component gets differentiated to 1 with respect to u, so that's just a term with k. So that's our r sub u. R sub v is similar, but now it's the x component which gets differentiated to 0, so there is no I vector in that, but there's 2v times j plus 2k. If we differentiate the z component, we get 2 if we differentiate it with respect to v. So these are our two tangent vectors, ru and rv. We have to compute their cross product, which if you do, let me just give you the answer, it's minus 2vi, so I hope you did compute this, minus 4uj and plus 4uvk. So that's the normal vector to the surface at any point where you take some values of u and v, you will get the normal vector to the surface at that point. So what we need is the normal vector at u equals 1 and v equals 1, so that will be minus 2I minus 4j and plus 4k. So that's the normal vector at the point which we care about. So that's our normal vector, and the point has coordinates. Remember, x, y, z coordinates. U equals 1, y equals 1. These equations give us these coordinates 1, 1, 3. So that's the point at which we want to find the equation of the tangent plane, and this is one normal vector to the tangent plane. So we can write that this is an equation for the tangent plane would be minus 2 times x minus 1 minus 4 times y minus 1 and plus 4 times z minus 3 equals 0, because this is the dot product of the normal vector with any vector sitting in the tangent plane. And that should be 0 as the normal vector is perpendicular to the tangent plane. So simplifying this equation will give you x plus 2y minus 2z plus 3 equals 0, or rearranging everything, so we express c, we get a half times x plus 1 plus 3 over 2 being equal to z. Okay, so that's the way to find the tangent plane to a surface. And next we'll look at the surface area and how that can be computed using double integrals. I hope you enjoyed this video, and I'll see you in the next one.